Hey there, math fans. Dr. Andy Lovelace. Here I'm going to talk about the intersection of a curve and a surface in 3D. As I've said in my previous videos, I think talking about intersections is a good way to get a feel for how curves and surfaces work in 3D and help you see the value of them and make it a little less mysterious. So I hope this is helpful. Check my previous video where I talked about the intersection of a surface and a surface. Here we're going to do what I think is the easiest of the types of intersections we do, which is a curve and a surface. I did make a short video motivating why that might be interesting to you. But I'm going to do 3 examples. 1, I'm going to find the point on a plane that's closest to the origin. 2, I'm going to find the intersection of something basically thrown in the air. This would be an equation that's very close to something thrown in the air and where it hits a plane. And then I'm going to do a weird spiraling thing, which is that thing on the right, and I'm going to find when it intersects a given sphere. I'm going to show you that all of those are fairly straightforward. I feel like most students would probably guess what to do just given these. But the fact that they're in 3D kind of scares people. And I'll show you some visuals. Okay, the first one probably has the most thinking involved because I always tell students that the way I draw a plane is always the same. I never try to draw it accurately in any way. The point of drawing, so sometimes students go, well, what's the point of drawing it? The point of drawing it is to have something to attach my brain to. Because for a plane, I know it has many points on it and it has a normal. And that normal is 1, 2, 3. The truth is, I don't actually draw a picture, but I do visualize that in my head the moment I see this. That's not really having to do with this section, but I'm just talking about this. And then they give me some point. Now, in this case, the point is the origin. So what does this have to do with this section, and why am I doing this first? Well, because if you walk directly to your plane, and let's say you walked through it, that's a line. And so this point we're trying to find, if you search online, distance to a plane, there's several ways to do this. What I like is this is a fairly simple approach that doesn't require I do any distances or anything. But what I'm asking for is that point. It's the intersection of a line and a plane. The actual picture here is this is the plane. It's tilted this way. And this is the origin. And I am trying to walk straight to that right there. I'm going to make one adjustment so it looks a little better. That's it. And so what I'm going to do is I'm going to draw a line that goes straight through it. At that point, I know what to do. So this is going to, for those of you that don't know how to find the equation of a line, watch my previous video on that. But we immediately write the equation of a line. We need a point that we know is on the line, which is 0, 0, 0. We need a direction, which is parallel to the line, and we can use that 1, 2, 3. So 1 times t, 2 times t, 3 times t. And the moment we write that, we're essentially done. All intersections are about combining conditions, and so we would like this x to be the same as that x. We would like this y to be the same as that y. We would like this z to be the same as this z. As I said, that's probably what, if I just gave a student this and gave them time, that's probably what they would do, even if they didn't understand, is they would combine. And then we solve. It's fairly easy to solve. I think in this case, you get 4t plus 9t. So let's see, that's 4 plus 9 is 13, and then 1. So it's going to be 14t equals 4. You're going to get t is 2/7. You're going to substitute this in for these, and there's your point. Your point is 2/7, 4/7, 6/7. It's that fast. So intersections of curves and surfaces don't have to be bad at all. In fact, they set up perfectly because the one parameter actually makes our lives great because it gives us a one variable equation to solve. Now, sometimes we need a solver, but that's always true about one variable equations. So I like that. So that's a quick application. Notice you could use this to find the distance from a point to a plane if you happen to have forgotten the formula in the book, which is another thing I like about this, because now you'd have the point, you could do the distance. Okay. Let's do another one. So let's do a more unusual one, maybe. I would say this is more realistic in the sense that You're starting to throw an object in the air, and it's going to follow this parabolic path. Okay? And your professor is sitting on the hill that's next to you. It's a sloped hill, resting, sunbathing. And you would like to hit him hard with a water balloon. And he's right there. How do you do that? That looks complicated. How do you find that point that's sitting right there? It's not complicated at all if you have the equations already. Now, if you don't have the equations already, then it is harder, but that's more of a physics question of what's the projectile? But we are done. These are easy questions. These are not something to be feared. If this is on a test, you go, oh yeah, I like these sorts of intersection questions. I just combine like I naturally would want to do. I'm trying to find the x, y, and z that satisfy both conditions. And in this case, I substitute all in. I'm going to get this messy equation, yes, 2 times whatever the z is, minus 10. This helps you see why the parameter, even if the parameter isn't something we're visualizing in the picture, why it is so useful. That's a quadratic equation. I'll save you from me singing the quadratic formula or factoring. Actually, this one factors nicely because you can factor it out, and one of the solutions is 0, one of the solutions is 2.85. That's actually exact what it is, so the answer is 2.85. I already knew one of the solutions was 0 because I'm throwing it from the plane. So here's the point where it hits. We can animate it. Here's the object. It gets thrown. And it hits. That's it. Notice I don't even need very much space to answer these. All right, so now I was just trying to think of another example. Let's say we had a sphere and we were intersecting something with it. So I just started to make something up that I knew would easily simplify. In general, you could take any curve. It just wouldn't necessarily simplify. So again, I made up this thing. I don't want to hide that. I made this so that this is going to simplify and we can solve it exactly. You might start thinking about why we can solve this exactly. But I don't want to focus on that because it makes it think like you have to have a trick to solve these. The technique would be the same even if these were much messier equations. You just would need a solver. But you still would use the same technique. Your job would be to describe the curve, substitute in, solve. Now, when we substitute in here, it's actually pretty nice because you're going to get the first one. I know you can't quite see that. Darn it. That's on me. I'll zoom out just slightly here and move something around. Okay, so substitute and solve. So in this case, what happens is you get 4 cosine squared of this mess. And you also get 4 sine squared of this mess, and you get t squared squared, so t to the 4th equals 21. And now can you see how I made it so this would simplify nicely? This right here, and you should be looking for this because we have a lot of spiraling problems in this course, is just 4. Think about why that is. If you factor out the 4, then it's sine squared plus cosine squared. And so altogether you get 4 plus t to the 4th is 21. Again, it's a made-up example. And then you subtract and get 17. I wanted that to be 16. I'm laughing because here's a mistake. So I did not make the numbers nice. It's the 4th root of 17. Let's change this to a 20. Now, sorry for this either. 20. I wanted this to be a 16. This is what a prepared person would have done. I worked it out. I just realized I hadn't changed it. I wanted t to be plus or minus 2. There's 2 solutions. So this needs to be 20. Okay. The interesting thing about that curve is it's this funny looking knotted spiral thing. It's always on the cylinder viewed from above. And that's because x squared plus y squared is a constant. The reason the other variable is weird is because it's like a parabola. Like it's spiraling while it's also a parabola. Like if you could see it in terms of just the z coordinate, it's like a parabola. But at the same time, it's spiraling. If I change some of the numbers to be smaller, you could more easily see the parabola. So it looks like a parabola from the side. It's just also twisting and turning at the same time. I made it turn really fast so that it was more exotic. That's it. Here's the sphere. And if I take those 2 times, and I should have said this here, the way you would finish one of these problems, you'd plug this in. But if I take a 2 and plug it in here, in here, in here, or a -2, those would be my 2 points. So I plotted those. One is there, one is there. That's it. Those are the only 2 intersections. So I just wanted to do some interesting pictures here, but that is not hard. The general theme in all intersections is to combine conditions. I never, ever say set equal because I've just seen too many students make mistakes. I'm substituting. It's the take it and shove it method. That's what all this solving is. But in this case, it's particularly nice because after you take it and shove it in, there's only one variable, and you can solve that one variable equation. All right, I hope that helps.